All right, nice work. You found video lesson 2C immediately after leaving 2B, or not to be. That is the question. Shakespeare humor. Anyway, so this is video 2C, lesson 2C. This will finish up the vision lesson. So go ahead and watch this. And then, as I said in the previous video, when you finish, you can head on to Schoology and answer the exit slip for lesson 2B and 2C. So let's go ahead and pick up where we left off. Refraction and image. Refraction means the bending of light. Since the cornea has a fixed shape, its focal length is also fixed, and its ability to refract light is likewise fixed. So that means your cornea out here is not going to, unless you have LASIK, it's not going to change its thickness. So that means the amount of light bending that it does never changes. It's fixed. It's stuck. So when we change the bending of light to focus as we look at objects, we do it with the lens, okay? In order to focus light that has already been bent by the cornea, the lens must change the shape. The amount of bending of light is determined by the thickness of the lens. So when you go to look at something far away, the ciliary muscles will pull on the lens and make it thinner, and that allows us to see objects at a distance. When you go to look at something close, the ciliary bodies relax, causing the lens to get thicker, and you're able to focus on close objects. Now, here's what happens when you get my age. As you get older, we're going to find out that your lens loses its elasticity. It doesn't bend as easily as it does in your youth. So when these muscles relax and try to let the lens get thicker, it doesn't get as thick as it used to, making seeing things at a close distance, at a short distance, making it very difficult. And that's why I have reading glasses, because now to see things close to my face is difficult, because I'm an old man. An increase in the curvature of the lens for near vision is called accommodation. The near point of vision is the minimum distance from the eye that an object can be seen clearly, and that is about 4 inches. And I can tell you right now, if I hold something at 4 inches to my face, I'm not going to be able to focus on it. It will be blurry. So, and it says right there, a distance that increases with age due to loss of elasticity of the lens. And I can tell you firsthand, at the ripe old age of, as I'm making this video today, at 50 years old, I'm telling you that this has changed for me to be about a stinking foot. So 12 inches, and that's anything inside of that, and I need to go get my readers. Convergence is the inward movement of the eyes so that both are directed at the object being viewed. So as the closer you look at something, the closer that something is to your face, your eyes will both move medially to focus on that object. When you look at something far away, both eyes are pointing straight ahead. And then once they're both parallel, you can't get them to go in opposite directions. So if you're watching this right now, give it a shot. Try to make your right eye look to the right and your left eye look to the left. You can't do it. Our brains aren't wired to be able to handle that kind of stimulus. Convergence helps us maintain our binocular vision and see in 3 dimensions. Our binocular vision is what allows us to judge distance. Okay, that is a key predatory trait. All predators have their eyes in the front. And some of you from elementary, maybe remember from elementary school, hopefully your elementary school teacher told you that the little saying is, eyes on the side, I need to hide. Eyes on the front, I'm ready to hunt. Hopefully you've heard that before. Refraction and image with nearsightedness, also called myopia, only close objects can be seen clearly. Light rays coming in from distant objects are naturally focused in front of the retina and appear blurry. With farsightedness, also known as hyperopia, only distant objects can be clearly seen. Light rays coming in from near objects are naturally focused behind the retina. So what happens, the retina in normal vision, the light going through cornea and lens here will be focused perfectly on the retina, which means those light rays will converge on the retina, giving the person a nice clear image. If someone has an eyeball that's the shape of the eyeball is a little too long, then if they are nearsighted or myopic, then the lens focuses the light and it strikes where the retina should be. So it focuses in front of the retina. Okay, so you give them a concave lens. This bends the light enough to compensate for that deeper eyeball and allows the light to then be focused on the retina. And if someone is hyperopic or they're farsighted, that's just the opposite. Their eyeball is shorter, and the retina should be back here, but it's way up here. And the light then, it doesn't get a chance to focus before it hits the retina. And it's trying to focus it behind the retina, and it just doesn't work because it hits the retina first. So they get a convex lens that bends the light enough to get it to focus on that closer retina. Visual transduction. Once light waves have been successfully focused on the retina, the information stored in that electromagnetic energy must be changed by photopigments in the photoreceptors into signals our brain can interpret, a process called visual transduction. So basically, light rays are converted into electrical stimulation that goes to your brain. The single type of photopigment in rods is called rhodopsin, whereas the three different kinds of cone pigments, and again, those three different kinds of pigments in the cone are going to be sensitive to red, blue, and green. Okay, color vision results from different colors of light selectively activating the different cones photopigments, and we can see many different shades and varieties of colors, and it all depends on the concentration of these three cones and what concentration they are stimulated. In daylight, regeneration of rhodopsin cannot keep up with the bleaching process, so rods contribute little to daylight vision. In contrast, cone photopigments regenerate rapidly enough that some form of opsin is always present, even in very bright light. So if you've ever walked out of the sunlight into a dark room, you've experienced this. You walk into the dark room and you cannot see. But if you wait and give your eyes a chance, the rods eventually they're bleached out in the sun, so they're not working. So you have to wait a few minutes, sometimes up to 10 minutes, for the rods to regenerate, and then since they're good in low light vision, your low light vision then kicks in. As a consequence, light adaptation from dark conditions to light conditions happens in seconds, but dark adaptation from light to dark takes minutes to occur, and in some cases up to 40 minutes for full adaptation of light to dark. Most forms of color blindness are an inherited ability to distinguish between certain colors. It results from the absence or deficiency of one of the three types of cones. The most common is red-green. And this doesn't, now I have to explain red-green color blindness. This doesn't mean that anything that's red or green is invisible to that individual. This simply means that they can't distinguish between red or green. And to them, anything that's red or green to someone with normal vision appears to be about the same color. And as best as I can tell, it's kind of a brownish color. Red and green are just brown to them. So if you were colorblind, if you were totally colorblind, and you go to look at this panel, and I were to ask you what number did you see, and if you can't tell the difference between orange and gray, then you would see no number. So you don't simply ask someone what color do you see, because they'll always be able to give you an answer, right? But if you ask what number, then it would take advantage of their ability to see color, and they would not be able to find the number 12. If someone is red-green colorblind, then the green dots in this slide that make up the number 7, and just in case one of you gentlemen is colorblind that's watching this, I'll outline it for you. There's a bunch of green dots that make a number 7. And if you're red-green colorblind, all of these dots appear to be the same shade, and you have no idea. that there's a number 7 in there. And here it is kind of in reverse. So instead of red and orange and yellow in the background, now the blues and greens are in the background, and we kind of have our burnt reds right here, making a number 6 right there. Okay, so that's how these color blindness panels are used to find color blindness. Okay, so that is going to be the end of lesson 2C. So as I was saying at the beginning, go on over, go to Schoology, take the exit slip that's over lesson 2B and 2C, and go ahead and finish that up. So good work, everybody. We'll see you later.